Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And in this lecture we will be looking into the concept of density of states function, which will be very important when we study cryogenic electronics, especially in cryogenic electronics, where when the temperature goes down to a very low value, for example 10 Kelvin or below or even 50 Kelvin or below, how the states, the states where the electrons occupy, how they vary will be known by this lecture, right. So, we will know what is the probability of finding an electron at a particular state at low temperature. So, with this let me start this lecture here, and the outline of this lecture will be, we will look into density of state function, also referred to as DOS in most of the books, and in overall you will find DOS. DOS basically means density of states. Then we will look into Fermi-Dirac probability function, right, also known as FD function. The same thing will be looking into the distribution function, and then we will come to what is the meaning of Fermi energy of an electron, and then we will look into the charge neutrality of the electron. So, basically this specific lecture will let you know that with respect to temperature and space, how is the electron occupying its states within a structure, especially semiconductors, right. So, let us first start with density of states, right. So, what does it mean? I will tell you. It looks complicated in this diagram, but you just hold on and you will understand what the idea is. So, we have already studied in our previous discussions that k, the wave number, or we can write down in terms of energy, E to be is equals to h cut square k square by 2 m, right. We have known where m is the effective mass of the electron, effective mass of electron. So, if you take care of it and you put it back, then as you can see from this equation, 2 me by h cut square is equals to k square, where k is the wave number, right. H cut is the modified Planck's constant, E is the energy of the electron, and m is the effective mass of the electron. Now, k is basically a wave number, right, is in a k space. It will have 3 dimensions of k. So, kx, ky and kz. Why? Because basically when you look at the value of k, it is basically a sort of a derivative of a velocity, and therefore, it can have the components in all x, y and z direction, right, and that is what is seen on the right hand side of the sphere here. So, you see here we have k, and that has been extended to kx here, ky here and kz here, and this is the spherical shape. 1/8 of the spherical shape will be typically given as the k value here. Now, if you extend this k, and I will not do the mathematics here, but this can be extended up to this formula, that is nx square plus ny square plus nz square, these are the quantum states, into pi square by a square, where a is basically the distance between two electrons. So, if we break it down, I get 2 me divided by h cut square equals to nx square plus ny square plus nz square into pi square by a square, and therefore, I can therefore find the energy, right, as h cut square pi square by a square into 2 m, right, this multiplied by nx square plus ny square plus nz square. Now, if I assume that ny and nz are 0, which means that the quantum functions on y and z axis are 0, then we can always write down this to be as nx square into h cut square pi square by 2 a square. And therefore, you see as the state or as the level n goes on increasing, there is a parabolic increase in the amount of energy which it contains, right. So, n1, if I write n1, then, and if I assume it to be unity, then E will be equals to h cut square pi square by 2 m a square, then E1, E2 will be equals to, will be 4 times, if I assume this to be as says say eta, then this will be 4 times eta. E3 will be what? E3 will be 9 times eta, and therefore, you can see that as the value of n increases, the energy increases in a parabolic fashion, right. And from here we will try to derive what is the meaning of density of states. Now, density of state primarily means, therefore, we are trying to find out how many number of states per unit energy in the conduction band or valence band are there, right. So, if I take 1 electron volt of energy, then how many number of states are available within that band is known as the density of quantum states, and we need to therefore find out the density of quantum states both in the valence band as well as in the conduction band. Now, if you look at the basic model, we have already seen in our previous slide that E will be equals to h cut square k square by 2 m. Now, if I plot an EK diagram, right, if this is energy and this is K, then as I told you E versus K. So, at K equals to 0, let us suppose ideally I have this value here. So, this is a K square plot, right, this is E and this is K. So, which means that for a single value of energy you can have two values of K, minus K plus K. We will neglect for the time being minus K at the time being, we will keep it plus K. What this shows is basically that this curve is shifted by some finite value to the top, and this is your conduction band edge value, correct. So, let me draw it for you once again here. I can show you here maybe. So, if I have this and this is my K value here and this is my E value, then if you look like this, this is the minima of E and this is referred to as, let me say, EC. EC is therefore the conduction band minima edge. So, if you remember in all our previous discussion, we had this conduction band and this valence band. So, we are talking about the energy at this particular point, at the edge of your conduction band. That is the point where your energy will be minimum at K equals to 0. Now, as the value of K goes on increasing and as you move to a higher and higher states, this shift takes place on this side. So, let us say K equals to 1, you get this, K equals to 2, you get this, K equals to 3, you get this, K equals to 4, you get this, and so on and so forth. So, this is K equals to 5, this is K equals to 0, which means that as the value of K increases, the energy states associated with it is there. And please keep in mind that as the K value increases, the effective value of energy also increases. Therefore, the separation between two energy states at higher value of K is larger. For a smaller value it is shorter, and for a higher value it is larger in a sense, and therefore, I can plot a graph between energy and K vector, and from there I can write down E equals to EC plus h cut square K square by Mn star. Mn star is the effective electron density. So, you learn one thing, that the lowest energy state, which is the edge of the conduction band, we will have the lowest energy state, and let us assume that to be equals to EC. Now, I will not go into details how they are calculated, but the density of the allowed energy states in a conduction band is given by this formula which you see in front of you. So, GEC is the density of the allowed energy states, and it is given as 4 pi 2 Mn square to the power 3 by 2 by h cube into E minus EC. Now, as you can see very well, when you put E equals to EC, right, this quantity goes to 0, implying that G of CE goes to 0, which means that the number of density states are 0 at the equals to 0, right. Now, as E value goes on increasing, so does the value of GC of E. So, this is the conduction band. So, conduction band was somewhere here, right. Now, the valence band will be here. So, let us assume that the K value has not changed for them. Then EV will have the maximum value, and as you go down, the energy goes on sort of reducing in a sense. Negatively, it goes on increasing, which means that more and more bound states are there, which means that within the valence band, you have always a bound state because energy is negative. If energy is negative, all the electrons will be at bound state, and we apply the value of GV of E, which is the allowed energy state for holes, to be equals to 4 pi to MP square by 3, where MP is the effective mass of the holes, MP, effective mass of holes. Which an interesting thing happens is that at E equals to EC and EV, both the cases the density of state is equals to 0, the effective density of state goes to 0, right. And that is quite an interesting phenomena which happens. I will just showcase a numerical example to showcase this problem statement. The problem is that you have to determine the number of quantum states in silicon between EC and EC plus KT, where T equals to 300 Kelvin, K is a Boltzmann constant. Now, the solution can be that the total number of electrons, I had density of, so it was density of states, right. If you integrate from EC plus KT, you get the total number of quantum states, and therefore, you put what, EC to EC plus KT 4 pi whatever the formula is, which we have discussed in the previous stage. So, this becomes 2 by 3 and this is 3 by 2 EC plus KT by EC. Solve it and I get number of states to be equals to this much, 2.12 10 to the power 19 per centimeter cube, which means that if you take 1 electron volt and try to find out the number of states per unit volume in the K space, it comes out to be 2.12 10 to the power 19, right, in the conduction band. And if you are told to find it in per meter cube, you can also do that from per meter cube. So, in most of the problems which we face in semiconductors, try to keep it in per centimeter cube. If nothing is asked from you, try to convert everything into per centimeter cube, not meter cube, right. But this numerical problem is to state that specifically you have to find in terms of number of states per centimeter cube, per unit volume. Well, so we have learned two things from now, and we learned new thing one again. The first two things which we have learned is that the density of states per unit volume of semiconductor per unit energy, how many number of available states are there. Higher the number of states, more probability of finding electron there if in the conduction band, more probability of finding in the valence band. We have also seen that when you go to the top conduction band edge, right, that is the zero energy state, so the minimum energy state, and as we move ahead we go on seeing a larger and larger number of energy for the states available there, and just the reverse is true for the valence band. Now let us look at the Fermi-Dirac probability function, right, and this is an interesting phenomena from where we will derive the Fermi-Dirac function and Fermi potential. Now let us suppose there are GI quantum states available, right. Forget about the word quantum, there are GI states available, G suffix I state available. I is the ith energy level, right. So ith energy level, suppose this is a ith energy level, and I am talking about the number of GI number of quantum states available in the ith energy level, and in the I have level 1, 2, 3, 4, 5, 6, so on and so forth till GI, right, and this can be found out by our previous discussion. Then the total number of ways of arranging Ni particles in the ith energy level is given by this formula. I think all of you can do it by simple permutation, right. So what I am trying to say is that in the ith energy level there are GI states, right, and GI is assuming it to be larger than Ni, where Ni is the total number of particles available in the energy states. So I have an ith energy state here, and there are n number of particles and there are g number of states available. So you will ask me how, in what possible ways I can arrange these GI number of particles in g particles in n particles in g number of states will be given by gi factorial upon gi minus ni factorial, right, and from here you can find out the value of the total number of ways. However, the total number of independent ways of realizing a distribution of Ni particle in the ith level will be given by this divided by Ni prime, Ni factorial basically. Ni factorial is the number of particle itself can be again redistributed within themselves. So when you multiply that, I get the actual number of independent ways of realizing distribution of particles, correct. What we have done, we have taken any say GI level, right, there are GI states available, ith energy state, and there are G states available within which there are n number of particles available in that ith energy state. Then the number of ways arranging Ni within GI is given by this formula, say this here, this one, and then if you want to look at independently how many states are available, it is given by this formula, Wi is given by GI upon n factorial GI minus Ni. And therefore what you need to do, just since there are the total number of ways of arranging these particles, indistinguishable particles within the energy state is nothing but the product of all the distribution. So what you do, you make a product from 1 to small n and then you make the multiplication here. So if you look at the parameter W, it tells me that how many total number of ways in which an electron can be arranged within a energy state, right, and n is the total number of electrons, right, available in the system. Therefore the whole problem boils down to, I have a conduction band, I have n number of electrons, I know how many states are available, how can I arrange electron in those energy states, what are the various ways of arrangement, and that is given by this formula which you see in front of you. With this, let me give you a small numerical statement and then we will go for the Fermi-Dirac distribution. Now the question is, determine the possible number of ways of realizing a particular distribution for this GI-Ni equals to 10 and GI-Ni equals to n. Please understand, here GI equals to Ni, and in this case it is GI is larger than Ni, right. So if I use this relationship where we want to find the unique ways of doing it, then what we get, GI equals to Ni equals to 10, we may note that GI, therefore GI minus Ni will be factorial 0, which is 1, right, and therefore if I solve it I get 1 as the answer. So the number of ways, independent ways available is only 1, whereas, and that is true also. Why? Because the number of states and the number of electrons are exactly the same, right. I am assuming that their states are not unique states, they are varying states, and therefore there is only one way by which you, and that is very simple, because there are, so it is like this, there are 10 electrons and there are 10, let us suppose, states available. I can do a one-to-one mapping easily and you can find only one form of probability of finding. Let us come to the next one, where GI equals to 10 and Ni equals to 9. There are 9 number of electrons available and the number of states available are 10. Then we find out, do the same formula once again, and then we find out the number of ways to do it is given by this one, right? And that's what you get out of it from that value 10. I get 10. So there are 10 ways in which you can arrange the particle, right? So more is the difference between Gi and Ni, till a point you will get larger number of ways, independent ways of forming this states, number of independent states, which is Wi, right? And from there you can find the value available to you. Okay, so let me come to the probability distribution. Probability distribution is, if I find the ratio of the number of particles per unit volume per unit energy state, and you divide that with the number Ge, which we have already defined, number of quantum states per unit volume per unit energy, that is defined as my probability density function. So how do you define probability distribution function or probability density function? Is the ratio of Ne to Ge, which is shown here, this one, and this is referred to as a Fermi-Dirac distribution. This is known as Fermi-Dirac distribution and is defined as the ratio of Ne to Ge. Ne to Ge is what? Ne is the number of particles per unit volume per unit energy state, and Ge is the number of quantum states available per unit volume per unit energy. When you divide it, you will get a number, right? And that is the probability density function, and that is given as f of E suffix of f, and is given by 1 upon 1 plus exponential E minus E of kt. Now this is where an interesting parameter comes into picture. E is the energy, of course you know, T is the absolute temperature, K is the Boltzmann constant. A new parameter comes, is known as the Fermi potential or Fermi energy. So it's E minus E of t, right? Now therefore, please look at this statement. This statement is very, very important from the understanding point of view, that the function is, this function which is f of E is called a Fermi-Dirac distribution function, or also defined as Fermi-Dirac probability function, and it gives me a probability that a quantum state at energy E will be occupied by an electron. So what does it tell me is, if E is the energy of an electron, right, then what is the probability that a quantum state at energy level E will be occupied? That is given by this Fermi-Dirac distribution. I will help you with a simple explanation and you will understand. Now you see, when E becomes equals to EF, then this quantity becomes 1 over 1 plus exponential 0, and therefore that becomes equals to 1, and I get 1 by 2, which means that the probability of finding the electron at Fermi level is 1 by 2, half, or 0.5, right? And therefore, if you plot Fe versus E in ideal conditions, then let me see if I have a graph or not for that one. I may be having, I will discuss it here. And let's therefore, so take that into consideration for your observation. Let me put this equals to E minus Ef by kt, and this is equals to f of E. And then let me plot this function. If I plot this function of Fe versus E, then I get this function. This is Ef, this is probability 1, and this is probability 0, which means that any energy state below the Fermi level, below, when I say energy low, will always be occupied, and energy states above Fermi level will always be empty, and therefore the probability of occupancy at Fermi level will be approximately equals to half. This concept is at T equals to 0 Kelvin. We will see later on what happens later on, but this is for a very simple straightforward way of saying it. Therefore, if I plot E versus Ge, we have already seen Ge in our previous discussion, right? Now the understanding of Ge, this is G of E, right? This is for conduction band and valence band, and you see it's a square root function. So if I plot the square root function and check here, if I plot E versus G of E, then I get the minimum number of states at EC equals to 0 almost, and as you go on increasing E, it goes on increasing in a parabolic fashion, because I have already shown you that energy versus G is basically a square root function. Similarly, if you look at the valence band, it goes down like this and the conduction band goes like this, which means that as the Ge value goes on increasing, I will have an increased value of the energy available with me. And please keep this in mind, the right hand side figure showing the Fermi energy change, right? Any energy state below Fe will always be occupied, and therefore will have a probability of 1. Any energy state above Fi will always be empty, and therefore the probability will be equals to 0. This is what I have drawn, you see. This is what I have drawn, you see, the same thing which I have shown. So if f of E versus E, if you do, this is the energy state which is giving you 1. At EF is goes to 0, and beyond this is still 0. Till value, whatever value, maximum value you want to take. Therefore, at T equals to 0 Kelvin, all the states till Fermi level will all be occupied. So if you, let us assume that E5 is my Fermi level on the right hand side, Fermi level, then all the states below that will all be occupied. You see, E1 has 1 state, 2 has 2 states, 3 has 4 states, 4 has 6 states, and so on and so forth, and all of them are occupied with the electron. So it's therefore the occupancy is 100%, fully filled up, electrons are there. Now let's come to the density of quantum states and electrons in the continuous energy system, right? So what we have seen is that at t equals to 0 Kelvin, if you plot G of E, right, versus EC, right, versus E, the graph which I got was something like this, if you remember. This was your, so this was your, if I do a plotting, this was your G of E, and then, no sorry, this was your E energy, this was your EC, and I was plotting with respect to G. I am just sort of making it twist, the graph is twisted, and so the x axis which was G of E was now converted to y axis, has been converted to x axis. So the graph has converted to this value, sort of this, the black color. This is the function of G of E. Now let's look at EF. EF is the Fermi energy state here, Fermi energy state here. If you look at EF here very closely, then the area under the curve here will give you the total number of field state available, and that will be nothing but integral from 0 to Fe, right, G of E dE. So G of E is nothing but the number of electrons per unit energy state. If you multiply it with energy state, integrate from 0 to EF, I will get the total number of energy, total number of electrons available. Now the right hand side figure shows the discrete energy states and quantum states for the same system at t equals to 0 Kelvin. There is a finite probability, so electron from E4 will be shifted to E5 and E3 will be shifted to E4, correct? This gives you a brief idea about the quantum energy states. So now let me give you a small sort of exercise which you can do yourself. If this graph would have been something like this and the E value would still remain the same, then of course the area under the graph, this will be extra area on the graph, and this will get added up where to n naught. So the number of electrons available will be larger, and that is true also. Intuitively, if you think higher the value of G for a fixed value of E, larger number of electrons will be available at a particular point, right? This gives you the concept of quantum states and occupancy. But keep in mind two things, that Fermi level is EF is the Fermi level where the probability of finding a free electron is 1 by 2 or half. Ideally at t equals to 0 Kelvin, all the states below Fe are filled up and all the states above Fe are empty, right? We will start from this in our next lecture.